So we're going to continue to talk about adaptive or specific. And like I was saying, when we talk about specific, we're saying that now there's real recognition of specific molecules or antigens. It's not simply we know now that it's foreign, it's that we know it's foreign and we know exactly what it is because we have cells that bind to it. This is coordinated and produced by T cells and B cells. What's another name for T cells and B cells? T and B. It ends with cyte. Lymphocytes, okay. These are not present at birth, they're acquired because you get exposed to antigens, and that's called active immunity. Active immunity, when you're exposed to the antigen, your body starts forming these particular cells or antibodies that react. Now, you can also receive antibodies in a passive form, but when you receive antibodies, you don't get long-term immunity because your body does not keep those antibodies like it does with active immunity. We'll talk more about that. So we can talk about naturally acquired, which means after you were born, you start getting exposed to these antigens. And again, an antigen is a foreign thing. It's non-self. Anything that's foreign that's non-self is an antigen that your body recognizes as foreign. And we'll talk more about an antigen because an antigen really is going to be a specific molecule that is on that foreign thing. And some foreign things could have several antigens. Your body could be reacting, say, on a bacterium to maybe 10 to 20 different antigens. It could be 10 different things on the cell wall of the bacterium. It could be something the bacterium produces. So contracting the measles gives immunity against future infections. Unfortunately, people out in the Northwest right now are acquiring measles very naturally. Artificially induced, this is what they should have done, develops after administration of an antigen, immunization, vaccination. So what we do in vaccines is to give you a dead or inactive pathogen, and this stimulates an immune response of your body to produce antibodies against that specific pathogen. And we'll talk more later on about why it does scare people. I mean, it is understandable why some people do have some fears of vaccination because of particular side effects that have potential. And I'll talk about the research on that. Okay, now passive immunity, there's two types, naturally acquired and artificially induced. Passive immunity is when your body's not forming its own antibodies. This is when you're being given antibodies. And remember, an antibody is something that reacts against an antigen. Naturally acquired is when you get it from the mother through the placenta or breast milk. Artificially induced is when you're actually administered antibodies. Now you've probably heard of a toxoid or an antitoxin. That is artificially induced passive immunity. We will give this kind of administration when you have got something that your body needs to react to very quickly, and we think your body will not react fast enough by itself. So like if you had a certain snake bite and had venom inside of you, certain spider bites. And there's some others too that we'll talk about later on. But again, if you have passive immunity, you don't form long-term immunity to it because your body didn't form those antibodies. So therefore, your body does not form memory B cells to produce its own antibodies. That's how you get real immunity, is your body forms memory B cells that will later on produce antibodies. Okay, so this graphic shows you how we divide up adaptive specific immunity into active and passive. Again, under both active and passive, you have natural and artificial. The difference is the artificial means basically we gave you a shot. Okay, active, naturally acquired basically means you got sick the old-fashioned way. Naturally acquired active immunity, you just got sick. And that's probably really one of the better ways, because your body does usually form some good long-term memory when that happens. Unfortunately, there are some things out there that may get you before you get it. And that's why we have artificially acquired active immunity. So artificially acquired active immunity is vaccination. Okay? So active immunity means you form your own antibodies against something. That's active. Passive, we just give you the antibodies. Everyone clear on that? Okay, some properties of adaptive immunity. Specificity. It does involve T and B cells, even though I keep talking about B cells because they're the ones that ultimately become plasma cells and produce antibodies. T cells also react. And certain T cells, like T helper cells, are important in getting B cells activated. And we'll come back to that too. But both T cells and B cells have receptors for a specific antigen. And responses of the activated T and B cells are very specific. They don't affect any other antigen. And by the way, this is one reason why, even if you already have immunity to a specific antigen, that you can get a different form of that infection again. This is why you have to get a new vaccine every year for influenza, because what happens with the flu virus is it mutates all the time. It just changes one component on its protein code. Just one component, it changes its antigen, and your body's immune system no longer recognizes it. And so your immune system has to go through the whole process again to go through activating new B cells and producing more antibodies. Okay, versatility. Millions of lymphocytes, each are sensitive to a different antigen. And by the way, you already have lymphocytes in your body that can recognize every antigen out there. It's just that you may have so few of them to start with that you have to get them activated before they can actually make a good fight against something. So once they're activated, the lymphocytes divide. They produce more lymphocytes with the same specificity. All the cells produced by the division of an activated lymphocyte we call a clone. We call that clonal expansion when we produce a lot of lymphocytes of the same specificity. Okay, another property of adaptive immunity, memory, which I have alluded to. The activated lymphocytes produce two groups of cells, the groups that attack invaders immediately, and then one group that remains inactive unless they're exposed at another incident later on. These are memory cells. They remember the antigen. They are able to come about in future attacks and react very fast, very strong. That's immunity. That's the immunity we talk about when we talk about being immune to something. It doesn't mean that that organism doesn't infect you. It means when it does infect you, you react so quickly you never knew you had it. Okay, so the properties of adaptive immunity: specificity, versatility, memory. Specificity, versatility, memory. And tolerance. Immune response ignores itself, but it targets abnormal and foreign non-self cells and toxins. And this can develop over time in response to chronic exposure to an antigen. And so you've probably heard of people building up tolerance to things over time. That after they've been exposed to so many times, I mean, you've heard about this, I think, with people that have maybe been bitten by certain snakes, that over time it doesn't really affect them anymore. Okay, so what were those 4 characteristics? Specificity, memory,
tolerance.
Tolerance.
I forgot the last one.
So it begins with a V. Versatility. Okay, and those are characteristics of what?
Immunity.
What kind of immunity? Specific or adaptive immunity. Okay. And what 2 cell types coordinate adaptive immunity?
B and T.
Yeah, B and T cells, or B and T lymphocytes. Which type of immunity develops when a child is given the polio vaccine? So what do you call it?
The administered one.
So first of all, is that active or passive?
Passive.
Are you being given the antibodies, or are you being given the antigen? You're being given the antigen. So is that active or passive?
Active.
Active, right. If you're given the antibodies, it's passive. Now, is that artificial or is that naturally acquired?
Artificial.
Artificial. So it is artificial active. Okay? Antigens either infect cells or they're processed by phagocytes. So antigens or antigenic fragments are displayed on the plasma membrane of some of these phagocytes. And this is called antigenic presentation, and it triggers an immune response. So you may have remembered I mentioned earlier that certain cells like macrophages, I mean, sometimes they just take in a foreign thing and they just kind of destroy it. But one of the things that they do also is they take in that foreign invader and they break out some of the pieces like its antigens and they redisplay it on the outside of themselves. It's like they're waving a flag saying, I found something. The T and B cells need to take a look here at this foreign thing. So this is antigen presentation. And so presentation of the specific antigens by those phagocytes like macrophages will stimulate cell-mediated immunity by T cells and antibody-mediated immunity by B cells. So macrophages help. So that's what they're showing here. So at the top we show the phagocytes being activated, T cells being activated, and then as a result of the T cells being activated, that often will then activate B cells. Now, some antigens will activate B cells by themselves without the T cells becoming a part of it. If T cells get activated, the T cells go out and find the pathogen, they attack them directly, or they release certain toxins that kill the microorganism, the antigen. In the case of the B cells, they will develop into plasma cells and produce antibodies that then attack the antigens. And we'll talk about the different ways that antibodies work. Okay, now, one of the ways this communication occurs between macrophages and T and B cells, and the way T and B cells recognize self from non-self, is by this complex that we find on your cells, major histocompatibility complex, or MHC. It is determined by chromosome 6. And placement of the antigen-glycoprotein combination on the plasma membrane is called antigen presentation. So what's going to happen is when that macrophage takes in that foreign invader and reads parts of that foreign thing, that antigen waving for the T and B cells, where it's displaying that flag is on an MHC complex. And therefore it's capable of activating T cells. So this shows antigen presentation using what we call class 1 major histocompatibility complex. So the viral or bacterial infection of the body cell triggers antigen presentation by class 1 MHC proteins. Okay, so the macrophage takes up those particles, redisplays them. The infection results in the appearance of the abnormal peptide. The endoplasmic reticulum produces class 1 MHC proteins to which the abnormal peptides are attached. The abnormal peptides are displayed by class 1 MHC proteins on the plasma membrane. So this cell that we're looking at here is a phagocyte. Okay, so this is a macrophage. So it brings in that foreign thing. It finds pieces of it that are the antigen that the T and B cells will recognize, and it redisplays it on its surface inside of the MHC protein. So if you want to look at it like, I don't know, a hand or something sticking out there holding that particle, come and get it. And then after the export to the Golgi apparatus, the MHC proteins with the bound abnormal peptides are transported to the plasma membrane. That's how it gets there. Oh, I went the wrong direction, didn't I? Okay. I went 5 before 4. But make sure you see the proper sequence there. It has to be packaged in the Golgi apparatus first, then transported by the vesicle onto the cell membrane and displayed as a class 1 MHC. But there are different classes of MHC proteins. Class 1 MHC proteins, these are present in the membranes of all nucleated cells. They're triggered by viral or bacterial infection of the body cell. Class 2 MHCs, these are present only in membranes of antigen-presenting cells. So these are the ones you find on monocyte macrophages, dendritic cells. Okay, so even your normal cells, if they take in certain organisms, they can display certain things as well, but antigen presentation really occurs on these macrophages and dendritic cells. So here's your antigen presentation with class 2. Same process. But this is still how, like in the case of MHC1, which was on the other picture, that's how your immune system knows if your normal cells are infected with the virus or some other foreign thing, because it does show it on the outside of it. So this shows a lymphocyte coming into contact with an antigen presenting cell, like a macrophage. Okay, so again, the MHC complex is kind of like that hand that's going to hold that foreign particle out. And that's how the T and B cells are going to see that foreign antigen. Again, all nucleated cells have class 1 MHC. Macrophages, monocytes, dendritic cells have the class 2. Okay, so now that an infected body cell has that fragment displayed on its MHC1, what happens after that point? This is antigen recognition now. So here's a T cell. The inactive T cell binds to a specific MHC antigen complex. The inactive T cell has receptors that recognize the class 1 or class 2. The T cell binds to the complex that has the antigen that the T cell is programmed to detect. And again, this is extremely specific. Only one kind of T cell is going to recognize one kind of antigen. Now, your T cells have CD markers. And these are the membrane proteins that are involved in antigen recognition. So where your cells and the macrophages have MHC complexes that present the antigen, the markers that recognize the antigen are CD markers. They're called clusters of differentiation. There's two classes associated with T cells. CD8 markers are the ones that are on cytotoxic and regulatory T cells. They respond to class 1 MHC proteins. So these are the ones that are going to respond to your normal cells that are infected. So cytotoxic and regulatory T cells are going to respond to MHC1, which is on your normal nucleated cells. CD4 markers are on helper T cells. So helper T cells respond to class 2 MHC proteins that are only on macrophages and monocytes and dendritic cells that are really antigen presenting cells. Okay, so here's what happens now. And we're going to look at a CD8 T cell. So in antigen recognition, again, we've got a CD8 T cell that encounters this class 1 MHC protein on the surface of another cell. So this is just basically a normal nucleated cell that's infected with the virus. It's redisplayed the antigen. The CD8 T cell comes in, recognizes it, and this activates all of these cytotoxic T cells. So we're going to proliferate, and now we have co-stimulation that activates more CD8 T cells. So physical chemical stimulation of T cells in addition to the class 1 MHC molecules. They say it's like a safety on a gun. It prevents T cells from mistakenly attacking your normal cells. And 3 different types of CD8 T cells are produced: cytotoxic T cells, memory T cells, and regulatory T cells. The cytotoxic T cells, they seek out and destroy abnormal and infected cells. And again, your cytotoxic T cells have what's called CD8 receptors that look for MHC1 complexes with the antigen, which means this is your normal cells, but they're infected. And what they're going to do, they're going to release perforins that perforate. You're going to have activation of self-destruction genes of the target cell for death, which is apoptosis. And we're going to have disruption of cell metabolism with lymphotoxin. Okay, the memory T cytotoxic cells are produced, but they do not differentiate further, at least at first exposure of the antigen. And at the second exposure to the same antigen, these memory T cytotoxic cells become full cytotoxic T cells. The regulatory T cells, they secrete suppression factors that limit responses of the other T cells and B cells. They act only after the first antigen exposure. So this shows all of the possibilities with these cytotoxic T cells. Okay, so again, the CD markers are the receptors that are on the T cells. And the CD8 marker is the one we find on cytotoxic T cells. The CD4 marker is the one we find on T helper cells. Cytotoxic T cells are looking for the MHC1 complex that we find on just normal cells. Okay. CD4 cells, or T helper cells, are looking for MHC2 complex so that they can help activate other T cells and B cells. We'll come back to that too. The So now let's talk about the CD4 cells. So these are basically the T helper cells. They first must be exposed to the antigens bound to the class II MHC proteins. So again, class II MHC proteins are found on the macrophages. Co-stimulation completes the activation. The next step, a lot of divisions. The daughter cells differentiate into active helper T cells and memory helper T cells. And the active helper T cells secrete cytokines, which further stimulate cell-mediated and antibody-mediated immunity. Okay, so here's our antigen-presenting cell, probably a macrophage. It has an MHC2 complex. It's taken in the foreign thing and redisplayed the foreign antigen. An inactive T helper cell comes in. It's a CD4 receptor. It recognizes it. Co-stimulation occurs, and then we have activation and proliferation of the cells. In the process of making more active helper T cells, we make memory T helper cells. Again, anytime you make memory cells, that's for the next time that you might be infected with that same thing. Okay, now, that was activated T helper cells. Now let's talk about how B cells become sensitized now. Preparation for activation is called sensitization with the B cells. Antigens are brought into the cell through endocytosis. Okay, so B cells can actually actively take in foreign particles themselves, and then they'll place the antigen on their surface bound to a class II MHC protein. But for full activation, they have to have a helper T cell to come in. So the helper T cell must have been activated already by exposure to the same antigen. The helper T cell binds to the MHC complex of the sensitized B cell, and now it's going to secrete cytokines that promotes more B cell activation. This causes a series of divisions in the B cells, and now we're going to form memory B cells. That's for the next time you're exposed. That's immunity. And plasma cells. And the plasma cells are the ones that are going to secrete antibodies. Okay, so again, the B cell has to have taken in that foreign antigen. It has to come into contact with a helper T cell that's taken in that foreign antigen. This activates B cells to become plasma cells that form antibodies. Let's talk about antibodies. You have one pair of heavy chains and one pair of light chains. And each pair has a constant segment. That's the base of the antibody molecule. And then you have variable segments. At the free tips, you have antigen binding sites, so this part will actually bind that foreign thing. And you have differences in amino acid sequences in that part that gives you variability. That's the part that recognizes all the possibilities of antibodies, and the fact that it has so many variations is why you can produce antibodies that will react or recognize anything. So this is what it looks like. It's kind of like a Y. This is the antigen binding site. This is the part that has the variable segments. So this part is the part that is always different based on whatever antigen it recognizes. That's the different part. This is the constant segment. And really, this is the binding site that activates complement that we talked about earlier, which is that cascade of chemicals that perforate cells. And also, this is the binding site for macrophages, basophils, mast cells. Okay, so when the antigen and the antibodies come together, when they bind, we call it an antigen-antibody complex. It's formed when a specific antibody molecule binds to the corresponding antigen molecule. It binds to specific portions of the exposed surface called the antigenic determinant site. And the bacteria could contain millions of antigenic determinant sites. And that's what I was saying earlier. So one bacterium could have a lot of different antigens, really. So you could form a lot of different antibodies to just one bacterium, because it's responding to each of the different pieces. Different types of antigens. You have complete antigens. They have at least 2 antigenic determinant sites, one for each binding site on the antibody. And then you have a hapten that's a partial antigen. They usually don't cause B cell activation. They can attach to the carrier molecules. They function as complete antigens. And antibodies attack both the hapten and the carrier molecule. So if the carrier molecule is normally found in tissues, the antibodies could attack the normal cells. And this is the basis for certain drug reactions like allergies to penicillin. Okay, so again, they're saying, you know, a hapten is just too small to recognize. And a bacterium can contain millions of antigenic determinants, like I said. And therefore, you can form a lot of different antibodies to a lot of different antigens on one bacterium. Okay, there's different classes of antibodies, also called immunoglobulins. And you may have heard this used in clinical settings. People being given immunoglobulins, it means they're being given antibodies. And it's determined by the heavy chain constant segment at the bottom. IgG, that's the main one, that's 80% of the antibodies. It's responsible for resistance against viruses, bacteria, bacterial toxins. IgE, this one attaches to basophil and mast cell surfaces. This is one that gives us a little trouble if you have allergies, hay fever. IgD, this is on B cells where it binds antigens and extracellular fluid. It plays a role in B cell sensitization. IgM, this is the first class of antibodies that are secreted after antigens are encountered. Production declines as IgG production increases. Okay, so this is always the first one, and then IgG takes over. And by the way, anti-A and anti-B, which are the antibodies formed against blood type antigens, are IgM antibodies. And then IgA, these are found in glandular secretions, mucus, tears, saliva, semen. They attack before the pathogens even gain internal access. Okay, so let's look at how the antibodies then react and the responses. So first of all, antibody-mediated response to the initial antigen exposure occurs, and this takes time to develop. The appropriate B cells have to be activated, then they have to differentiate into the antibody-secreting plasma cells, so this takes some time. And if we look at antibody titer, which is the levels of antibodies in blood, it doesn't peak until 1 to 2 weeks after the initial exposure, so this is why it takes time to get over certain infections. And over time, the levels decline. So as we were saying earlier, IgM is the first antibody that's produced, and then IgG takes over. Again, notice the time lapse there. It does take a while to reach that maximum response. Now, secondary response, triggered when the antigen is encountered again. More extensive, it lasts longer than primary response, your antibody titer increases very quickly. It reaches the higher concentrations. And the reason why you have immediate response is because you have memory B cells already. And it appears even if the second exposure is years after the first, because memory cells can survive 20 years or more. Now, for some types of infections, memory cells don't last that long, and that's why you have to be given new vaccinations every so often, or boosters. Okay, this is secondary response. Big difference. Very quick. Notice, in days. That's why you don't even know you have the infection the second time. As long as it's the same antigens, the same organism, the same virus. Okay, so we talk about antibodies attacking these things. How do they do it? Well, there's a lot of different ways antibodies work. Number one, neutralization. The antibodies occupy the binding sites on the virus and the bacterial toxins, and it prevents them from binding. So it basically keeps that organism from even attacking your cell. It can't bind to it. So that's one thing that antibodies can do, that's neutralization. Two, prevention of pathogen adhesion. IgA antibodies and glandular secretions cover the bacterial viruses and prevents any adhesion to even tissues or any of the cells. Three, activation of complement. That's that chemical cascade that basically perforates that foreign thing. Stimulation of inflammation. So the antibodies can stimulate the basophils and mast cells to release chemicals like histamine, leukotrienes, and other things that cause us all these other problems, but there's a reason. There's opsonization. Sometimes these antibodies simply coat a pathogen and it makes them more recognizable by like macrophages and other phagocytes to take them in and engulf them. And it simply attracts other phagocytes anyway, in more of a chemical way. So attached antibodies attract eosinophils, neutrophils, macrophages. So that's 6 ways that antibodies affect the antigens and foreign things. So antibodies don't just react one way. There's 6 ways antibodies react. I'm sorry, 7. I forgot about this last one. This is important. This is the whole reason that the blood typing works. Sorry about that. Precipitation and agglutination. The antibodies can bind to antigenic determinant sites on the adjacent antigens, so it basically ties up those organisms so that they can't do anything. It forms insoluble complexes, that's precipitation, or it forms immune complexes from the surface antigens, that's agglutination. Again, that's what you see in blood typing tests, but also a problem in transfusion reactions. Okay, so this shows you all of those possibilities. Okay, let's talk about some hypersensitivities or allergies. This is when you have an excessive immune response to the antigen. It's a quick cellular activity response. Your antibody titers are really high. And unfortunately, your neutrophils are cytotoxic. T cells can destroy your normal cells. The antigen-antibody complexes trigger inflammation. The antigens trigger allergic reactions that we call allergens. In this case, the organism or the antigens are called allergens. And this happens upon initial exposure to the allergen. We have sensitization, activation of B cells. That leads to lots of IgE production. That's one of those immunoglobulins. And in this case, these antibodies bind to certain cells like mast cells that release a lot of histamines. Any subsequent exposure to the allergen, you get a massive stimulation of the mast cells and basophils. You have a lot of localized systemic reactions like swelling, People that have respiratory problems, you could go into real breathing problems, anaphylactic shock. So this shows a basic first exposure, and you form the IgE antibodies. Okay, there's also in immediate hypersensitivity, rapid severe responses like in allergic rhinitis or hay fever. Inflammation of nasal membranes could affect 15% of the US population. The response is restricted to the body surface. And the body's response to the immediate hypersensitivity we call hypersensitivity reaction. These reactions could be localized, which means right at a specific area, like an allergen at the body surface, where you have localized inflammation, pain, itching. Or it can become systemic, where it's in the bloodstream, causing itching, swelling, difficulty breathing, like in anaphylaxis. And again, a lot of that is caused by the chemicals being released, like histamines and leukotrienes. In anaphylaxis, this is systemic. The mast cells react. In severe cases, you have peripheral vasodilation. This causes a drop in blood pressure, circulatory collapse, anaphylactic shock. So any exposure to antigens can trigger specific and non-specific defenses. Neither branch really does work alone. A lot of times those activities from each of the branches helps the other, enhances them. And responses will vary based on the antigen type. This shows all of those connections. So let's look at one specific integration. So bacterial and viral infection. So if we want to overcome a bacterial infection, in this case, most effective defenses involve phagocytosis, an antigen presentation by antigen-presenting cells. Okay, so you have both T cells getting involved and activation of B cells. Cytotoxic T cells and natural killer cells can be activated by the direct contact with virus-infected cells. Also, antigen presentation occurs, which activates these other cells, T cells and B cells. Okay, there are some disorders related to immune responses. Autoimmune disorders, which means reacting to yourself. So malfunction of your self-recognition system. Activated B cells can make antibodies against yourself or the tissues. These are called autoantibodies. It could result from similarities of the foreign antigens. Example, they give proteins in measles virus contains amino acid sequences that are very similar to the myelin proteins that are on your nerves. So the antibodies target the viruses, can also target the myelin sheaths. That's what they think is a mechanism for multiple sclerosis. Your risk increases if the person has unusual types of MHC proteins. Here's some examples of autoimmune disorders. Thyroiditis, autoantibodies against thyroglobulin. Rheumatoid arthritis, the autoantibodies attack the connective tissues around your joints. Type 1 diabetes mellitus, that is an autoimmune disorder where you attack your pancreatic islet cells and you don't produce insulin anymore. Multiple sclerosis, where you attack your own myelin of your neurons. Now, unfortunately, if you get some kind of transplant, these immune reactions also work against the transplant, so you can have rejections. The recipient cytotoxic T cells can become activated and attack the MHC proteins of the donated material. Reduction in the immune response, sensitivity, or immunosuppression by drugs can help in this case. For example, we can use cyclosporin to inhibit helper T cells. You can have hypersensitivities, though, also in relationship to that. There's also inadequate immune responses in certain immunodeficiency diseases that result from if you have problems with lymphoid organ and tissue development. Infection with a virus can depress your immune function, like an acquired immunodeficiency syndrome or AIDS. Also, treatment with or exposure to immunosuppressive agents, radiation, or drugs. AIDS is caused by human immunodeficiency virus, HIV, you probably know. And in this case, the virus actually binds to the CD4 protein and infects helper T cells. So one of the big problems with AIDS is it actually attacks the very cells that protect you. So the infected cells synthesize or release new viral proteins. Helper T cells are destroyed by the virus or the immune defenses, and therefore it impairs your cell-mediated and your antibody-mediated responses. So if you don't have helper T cells, you can't activate your B cells. And also, but your suppressor T cells are not affected in this case. So overall, what happens is your body becomes vulnerable to other infections. It is spread by contact with body fluids. It infects 33 million people worldwide, about 2 million deaths each year. We do have much better treatments now. I mean, I think I mentioned to you before, there was a time, I remember when we first heard about AIDS, like when I was in high school, it was really a death sentence to people. They were very scared of it, big epidemic. A lot of people are able to live pretty normal lives now. Unfortunately, as you get older, you do have reductions in your immune activity. Immune system's less effective with age. Your thymus shrinks. You have increased susceptibility to viral and bacterial infections. T cells become less responsive. Fewer cytotoxic T cells respond. The number of T helper cells are reduced. Your B cells are less responsive. So the antibody levels are slower in rising to antigen exposure. So as people get older, there are certain vaccinations that are recommended, like the pneumococcal vaccination is definitely recommended in people as they get older, or
Shingles.
Shingles is another one that's recommended. Age-related also includes increased incidence of cancer because natural killer cells are reduced. Your immune surveillance isn't as good. I've always been told this by science people that work in the medical field. You know, if you live long enough, you will get a cancer. There's like no way of getting around it. As long as we live now, it's like some incidents have increased because you live longer. Okay.